Okay guys, I'm going to go run through a short video. A few of you missed the class this morning because Zoom was playing up. Okay, so what we did was we moved on from sort of being able to draw our Born-Haber cycles, okay, into being able to actually do calculations based on Born-Haber cycles. Okay, so hopefully you should be able to see the screen in front of us at the minute. Okay, this is your class notes, so please make sure that you have got these. Judging on some of the responses this morning, people either haven't printed these out, haven't been reading through them, so they really are very, very important. Okay, in order for you to actually understand what's going on. Okay, so make sure, especially pages 1 to 7, that's the introductory pages before you even get to the calculations. If you don't understand what's going on pages 1 to 7, then it's really going to be very, very difficult for you to actually do the calculation. In fact, it's really only pages 4 through to 7 that's the new stuff. Okay, at A2, the rest of it is generally revision of AS chemistry. Okay, so I'm going to go to page 5 here, which is really, really important. It's a page of the various different definitions. Okay, and you really need to sit down and learn these definitions because you're applying the definitions to write the Born-Haber cycles and then to do the calculations from the Born-Haber cycles. And unfortunately, if you don't know the definitions, being able to do that becomes virtually impossible. Okay, so in class this morning, we went over these. Now, a lot of them are pretty much from AS chemistry, but there are a few of them, if I just bring your attention to them, that are new for this year. So please make sure that you learn them. So the standard enthalpy of atomization there is one which is new this year. Okay, and we talked this morning about the fact that the standard enthalpy atomization was the energy change whenever you make 1 mole of gaseous atoms. Okay, and what we did this morning was we compared that and looked at the pitfalls whenever you were comparing that to the bond association enthalpy. So specifically, atomization is only ever the energy involved. So if, let's say it might be X kilojoules there to make 1 mole of gaseous atoms. The bond association energy also makes gaseous atoms from 1 mole of gaseous molecules in this instance, okay, or from the element. Now, in this instance, the bond association will make gaseous atoms, but it's going to make 2 moles of gaseous atoms for something that's diatomic, for example. So when we're writing our Hess's law cycles, let's say it's for something like magnesium chloride. Now, magnesium chloride requires 2 ions, gaseous ions of chloride, 2 chloride ions, in order to go through that Born-Haber cycle. So if in the question, in the data that they give you in the question, they happen to give you enthalpy of atomization of chlorine, well then you would have to take that, if it's X kilojoules here, and that would have to be multiplied by 2 because you would need 2 gaseous moles of chlorine. If, however, in the question, okay, they give you the bond enthalpy for chlorine, which does give you 2 gaseous moles of chlorine atoms, well then you just multiply that by 1 or keep it as it is for your calculation. Now the flip side of that then, I guess, is if you were dealing with a compound like excuse me, like sodium chloride, and obviously in sodium chloride there is only 1 chlorine ion in there. So in this instance, if they give you the bond association energy down here of chlorine, okay, just tidy this up a little bit here. Okay, so if they give you the bond association of chlorine in this instance, okay, well then you would actually have to take that bond association for the purposes of your calculation and divide it by 2 because you only want 1 mole of chlorine, whereas bond association energy will give you 2. If they give you enthalpy of atomization of chlorine for something compound like sodium chloride, well that's fine, you just keep it as is, sodium chloride 1, okay, just 1 atomization of chlorine there, okay. Right, so hopefully that makes a bit of sense. We covered that this morning. The other thing we covered whenever we were doing our calculations was, let's say we'll go back to magnesium chloride again. Okay, now in magnesium chloride, you will know that that has to be made from magnesium ions. And we would start with the gaseous magnesium ions, and we would start with magnesium solid. So in order to get from there to there, you have to lose 2 electrons. So you're looking there for, in that energy change in the Born-Haber cycle, the first ionization energy, and you have to add the second ionization energy to that. Okay, a few times students get a little bit confused and they go, well, it's a 2 plus, so I take the first ionization energy and multiply it by 2. That's not what you do. It's the sum of the first and the second is what you need there. Likewise, if we go down to what is a new energy change for A2 chemistry, the electron affinity, which wasn't on the AS course, you have electron affinity. So the first electron affinity is whenever a compound gains an electron to this, will apply to your non-metal. So it's whenever 1 mole of gaseous atoms gains 1 mole of electron, it becomes 1 mole of gaseous -1 ions. So that if it was, let's say, a chloride ion, so if I'm something like sodium chloride or magnesium chloride, well then I only need to take into account the first electron affinity value, whatever that is. Let's call it X kilojoules. Now, if it was making magnesium chloride, in there you have 2 chloride ions, so you would have to take your first electron affinity and multiply it by 2. Alright, so just be a little bit cautious of that. If, however, it was, let's say, something like magnesium oxide, and you know that oxide ions are 2 minus, well then you've got to take the first electron affinity, okay, so the first EA, and then you've got to add to it the second electron affinity, because here you're going from X to X minus, and then down here the second electron affinity also, where you've got the X minus gaining another electron and becoming X2 minus. So there's another little pitfall that you would need to be careful of there. So for sodium chloride, it's nice and simple. It's the first electron affinity multiplied by 1. That's nice and simple. For magnesium, you have 2 times the first electron affinity because you've 2 chloride ions. And if it's something like oxide ions where you've got 2 negative, you've got the first and second electron affinities, both that you need to bring into play there. Okay, so again, those are just things that we spoke about this morning, that when you're doing your Born-Haber calculations, you need to be careful that you cover or you don't use the wrong values, and if you do have to multiply up or divide down, that you do that. All right, okay. So we'll move down here to looking at a few of these Born-Haber cycles and then doing the calculations. So there's some tasks there which you could do. Just write the equation including state symbols. And I did stress to the boys this morning that when you're doing the Born-Haber cycles, because all these steps in the Born-Haber cycle are definition based, i.e. the definitions that I have on the board at the minute, okay, then your state symbols are really, really important. They have to be in there. Okay, if they're not in there, you'll lose marks. You could very quickly lose 3 or 4 marks. Okay, so you're asked in this question here, and I'll do this for you just to give you an idea of what you should be after. So that's a Born-Haber cycle for that was sodium chloride. Okay, I'll do it actually for magnesium oxide here because that's a bit more difficult. It kind of covers all of our bases. Okay, so the first starting point that we always do is, or that I would always do anyway, is I go down to the down here and I start about here with my magnesium solid. And I'm reacting that with oxygen gas. Okay, and I'm making my magnesium oxide salt. That's the energy change. Essentially, that's the reaction. If you were comparing it to Hess's law from last year, that's the reaction that you're actually trying to investigate and look at the energy change involved in that. Now, again, this is why you need to know your enthalpy changes and your definitions. Well, that's the enthalpy of formation, making a compound, 1 mole of it, from its elements in their standard state. Now, there's one thing I just need to be cautious of there. Okay, it is a half O2. Now, some people might write Mg solid plus O gas. That's wrong because that would not have the oxygen in its standard state. Okay, so that's the enthalpy of formation. If we look at a Born-Haber and compare it to Hess's law, this is exactly why the two things are comparable, except this is obviously for ionic compounds. We're starting there and we're going to there, but we're going via a different route. We're going via this route here. Excuse my wobbly hand. Okay, so the key thing here is then that the delta, when you're doing your calculations, the enthalpy of formation is equal to the sum of all the other delta H values. Now, the only fly in the ointment there is that the lattice enthalpy is going in the wrong direction, so it's minus the lattice enthalpy. And we can rearrange that equation then to find out any of these unknowns that are in here. Okay, so just bear that in mind, guys, whenever we come to later on to doing the calculations. Okay, because that formula, that little equation there, where we're applying that Hess's law principle, is absolutely vital for doing the calculations. Okay, let's get back to drawing our Hess's law for magnesium oxide. Now, generally what we do is we deal with the metals first and we deal with the non-metals second. So let's say the first thing I need to do with the metal is I need to turn it into the gaseous atom. So I need to carry out enthalpy of atomization. So that's Mg goes to a gas now, plus half O2. We're not going to deal with that yet. Okay, then we keep dealing with the metal. We've got to atomize it. We've got to turn it into gaseous ions, of course. Okay, so we do first, I'll just do first ionization energy first, and then I'll come to the second one. Okay, so that's plus. Now, remember I said earlier, state symbols are key. They must remain in. Now, I have one electron, that has been lost from the magnesium, so I need to account for that. I can't ignore it, okay, or leave it out. It's like anything, it has to be balanced. All right, so that's my first ionization energy. And then remember, magnesium is a 2+ ion, so I've got to get to second ionization energy. Keep my state symbols in. I've now got 2 electrons that I need to deal with here. Okay, and I have half O2 gas still. All right, the next thing that I need to do, so that's the metal done. Okay, I've got it to 2+ gaseous ions. Okay, all done. Now I need to deal with the non-metal, and the first thing that I do with the non-metal, keep my state symbols in and keep my electrons in, nothing's happened to them yet, is I atomize it as well. Okay, I've got to break all the bonds in that covalent structure. Okay, now some student, and we did speak about this morning actually, why do I have to atomize, or why do I have to turn it to a gas before I can ionize? Well, if you think back to your definition, and again stressing the point that definitions are so key, if you think back to your definition, the ionization energy is built on the gaseous atoms. So it's turning gaseous atoms into gaseous ions. So I have to have them as gaseous atoms first. I can't ionize before I atomize. Okay. All right. So going from here to here. Now we need to be a little bit careful depending on what values the examiner gives us. That is the enthalpy of atomization of oxygen, or it is half the bond enthalpy of oxygen. Remember, the bond enthalpy is breaking all of those to give you 2O gas. Okay, whereas atomization is just making 1 mole of gaseous atoms. Right, some of you here on the ball may have noticed that this arrow now is going down, which means that it's an exothermic process. So that exothermic process is going down to the first electron affinity. So the first electron affinity of anything is always exothermic, gives out energy, gaining the first electron. We'll talk about why the second one is endothermic in a wee second. Now, key thing here is we've lost an electron. So we'll go from 2 electrons up here down to 1 electron, and we've got a -1 on our oxygen. Now, this arrow is now going up again, implying there we've got an endothermic process. Okay, and that endothermic process is the second electron affinity of oxygen. So again, now both my electrons are now gone. Okay, so the second electron affinity is negative, and the first electron affinity down there is first electron affinity is exothermic, second electron affinity is endothermic. In other words, it requires energy. Now, why does it require energy? Okay, well, if you're on the ball, you might have noticed that the oxide here is -1, and you're adding to it the second electron from the magnesium. So you're going to have negative to negative repulsions there. Okay, that's the reason why you have to overcome those repulsions, and that requires the arrow to go up because it's an endothermic process. Right, so we've got the whole way nearly to the end, we've got our gaseous ions. Our gaseous ions come together and we have our lattice enthalpy then. Okay, and if you look at it, that is lattice enthalpy of dissociation. We're breaking up the lattice. So if we're asked to calculate this, because it's dissociation, it'll always be endothermic. Alright, the way I used to do these in school was I ignored the fact, and I think this is the best way to do them, to be honest, I ignored the fact that this was against the grain, okay, and I just did the fact that all of the energy changes are equivalent to the delta HF, and then if I was asked to calculate my lattice enthalpy value, I just changed the sign on it at the end and made it positive. Okay, but it's purely up to you how you do it. Right, so that's everything has been drawn out. Okay, I've covered most bases there because magnesium oxide is a 2+ and 2-, so it kind of covers all your first and second electron affinities being needed, first and second ionization energies being needed, and all those possible pitfalls that you might end up in. Right, so we've got the various different bits of information down here, and we're being asked to calculate out the lattice enthalpy up above. So if we just remember that very quickly, and this is again is equal to the sum of all the other energy changes. All right, so let's go and apply and put our energy changes into this. Right, so our enthalpy of formation here is given to us as -642. So -642 is equal to the enthalpy change of atomization for magnesium is 150, and it wasn't times by 2 or anything, it's just as is. First ionization energy of magnesium is 736. The second one then, which we've got to add on instead of multiplying the first one by 2, is 1450. The enthalpy change for the atomization of chlorine. Okay, so if you think about oh, sorry, I've gone into magnesium chloride. Sorry, I'm doing the wrong one. Ignore me, please. Let's go back up here to the magnesium oxide one, which is the one that I'm supposed to be doing. Okay, and let's plug in these values. Okay, right. So these values are given to us in shorthand, whereas down below they were given to us in more detail. So let's do again. Let's find our enthalpy of formation here. So our enthalpy of formation is down at the bottom, delta HF. So that's -602. You'll actually notice that's a little bit different from the other one, which examiners tend to do. All right. First, atomization of the magnesium is 148. Atomization of the oxygen is 249. Okay. So they haven't given me bond enthalpy. They've given me enthalpy of atomization, and I'm multiplying that by 1. Okay. First and second electron affinity of magnesium is 739 plus my 1451. Okay. First electron affinity of oxygen is -141, so plus -141, or okay, and the second electron affinity is an endothermic. Okay, plus the lattice enthalpy. Okay, equals that. Okay, so all I got to do now is take my. I'll just do the calculation here to work out the sum on the right hand side. Okay, so I have, let's do 602 equals 3244. Okay, and then we've our lattice enthalpy there, so minus our lattice enthalpy. Okay, so I have my magnesium oxide, my lattice enthalpy for my magnesium oxide sitting at 3, 2, 4, 4, 4, 6, 7 is rather a hefty number of 3846. Okay, and that's kilojoules per mole, and that is endothermic. Okay, so pretty big, but you'd expect that because remember, magnesium is 2 plus. It's very small. It's highly charged a big high charge density, like we did in class last week. And the oxide is very small also with the 2 negative ions. So you have 2 small ions, one of which is 2 plus, one of which is 2 minus. Okay, so that's where you would anticipate your magnesium chloride being. Right, I'm going to go down to the next one here. Okay, so I'm going to skip out the next one. I'm going to go to the sodium oxide one. And the sodium oxide one, I'm doing that just because it will create a few issues that we haven't seen before. It's not particularly difficult, but it's one that we haven't done. So, all right, so I'll draw it out just to make sure that we're still sort of on the ball and in terms of knowing what's going on. So I always start with the enthalpy of formation. Okay, so we've got sodium oxide. Just to remind you, the formula of sodium oxide is Na2O. Alright, so we've got to start with the elements in their standard states. Okay, so remember, therefore it's half O2. Now, the enthalpy of formation will go to making 1 mole of the ionic compound, just delta HF. We've already got some numbers here. We can probably start popping them in. Enthalpy of formation here, so we've got minus 416. So it's a good idea just to pop the numbers in. Right, again, same thing again. I would try and deal with the metal first, and you've always got to atomize it first. Okay, I will get to the non-metal in a second. So again, that's delta H atomization of the sodium, and if we look up above there, that is 109. I was very kindly told you to remember, or reminded you to multiply that by 2, because remember it's in kilojoules per 1 mole, but we're I haven't put that in. We've got 2 sodiums. Okay, because of the formula Na2. Alright, so that's the sodium atomized. Now I need to take that sodium and ionize it now that I've got it as a gas. Okay, so keep my state symbols in. Each one of them has lost an electron, so I need to account for 2 electrons there. Okay, I'm not going to do anything with the oxygen just yet. We'll get to it in a second. So that's the first ionization energy. Okay, that's 494, but remember there's 2 sodiums being ionized, so we're going to multiply that up by 2. Alright, then we've got, so we'll keep our sodium as is and our electrons aren't going to go anywhere just yet. Okay, remember there's 2 of them. Okay, we need to atomize our oxygen now, so we go to O, gas. Let's see what they've given us up here. Enthalpy atomization of oxygen, so we don't need to do anything with that. That's 248. We do need to get rid of that little 2 there. That shouldn't be there. Okay, right, so that's our oxygen all sorted. We need to just now start to do the electron affinity of that. So remember, first electron affinity is exothermic, so we're popping back down again. Alright, and that brings us to 2 sodium gas, plus we're only going to have 1 electron now, because remember we're going through the process of making oxygen ions, and they'll be 2 negative, but we're at the minute we're just at the 1 negative stage, so that's the first electron affinity of oxygen, which is minus 142, and then we're back into endothermic processes for the second electron affinity of oxygen, so Na plus, still keeping an eye all the time, guys, and I'm putting my state symbols in. Really easy to forget to put them in, and now we've got, oh, that's a 2 negative, and it's still a gas. That's the second electron affinity there. Okay, so that's 844. Alright, we've got our gaseous ions. Okay, and then finally we have our lattice enthalpy, which is what we're being asked to calculate. Am I right? Yeah. Okay, so we go through, remember our little formula from earlier where the enthalpy of formation is the same as all others. And that makes sense because if you look at it, I'm starting there and I'm going to there, but I'm simply going via this route. Okay, so that's why that little formula stands up for us. So that tells us that minus 416 is equal to, well, it's equal to all of these. Let me try and, so multiply my 109 by 2 is 218. I multiply my 494 by 9, so that is, here we go, 988. Testing the mental arithmetic. Okay, we have 248 for the next energy change. We don't have to multiply or divide that. We have minus 142 for the next energy change. Okay, we have up to 844 for that. And then minus our lattice enthalpy. Okay, so we'll just work out what, excuse me, what is this term. Okay, do it quickly on my calculator here, try not to make any mistakes. Okay, so I have that, if I haven't punched anything wrong in there, sitting at 2156. So my minus my lattice enthalpy, so that comes across as 416. So my lattice enthalpy for sodium oxide here, I have as positive, remember it's endothermic, 2572. So I'll sort of check that on my calculator at the end just to make sure that I'm right. I think I am. Okay, kilojoules, sorry, per mole. Okay guys, look, hopefully that sort of gets the picture across. If there's any of the ones that you can't do, that's what we did in class this morning. So for those of you who missed it, that should be you pretty much up to speed with where we are. I've given you some questions to do, and that will test you on this material also. Okay, all the best.